All right, so let's do these last two problems. This problem right here says, at what distance in kilometers is an object if its parallax, as measured from either end of a baseline, which is 4,652.6 kilometers in length, of course, so that's the length of the baseline. The parallax is 1.08 degrees, and so it's already in degrees. Right, so of course we use this formula. We didn't even have to change the parallax, right? It's the same units. And so this, and let's say that on the test, if this was says something like round to one place past the decimal, this would be the answer that you get here. And let's see that on our calculator. All right, so there it is. Actually, I'm going to show you two different ways to do this on this particular type of calculator. All right, so I'm going to do it the way that we did it before, 180. I mean, it's the same thing, but it's just done slightly differently. 180 times 4,652.6, and then divided by, remember, we're dividing by both pi and 1.08. So I'm going to use parentheses, so divided by pi. And then, the pi is times 1.08, 1.08, and then I close the parentheses. And so I should get this number and then rounded to one place past the decimal. So there it is. So it's 246,828. And then, of course, if it's rounded to one place past the decimal, it would be 0.1. Right, because it's there's a 9 in the hundredths place. All right, so let's see that one more time. Just done slightly differently. So we're going to just say 180 times 4,652.6. All right, so we do that, and then let's say if I divide it by pi, so I'm not using any parentheses here. So you have to hit equals. And then you take that number right there divided by 1.08. And of course, it'll give us the same number because mathematically we just did the same thing. All right, and there it is. And then, remember, rounding to one place past the decimal. All right, so we've done the problems. So you might have a sneaking suspicion that there's going to be a few parallax problems on there. And of course there are. The next one is using Newton's. So we'll get rid of we don't really need the calculator now. All right, so let's set this up. So Isaac Newton came up with this thing called the universal law of gravitation, and so this formula describes it. This picture is supposed to draw, although the error. So it should be the distance here should be from the center of one mass to the center of the other. Okay, so I didn't draw it very well. I can't draw a straight line. Anyhow, that's the idea. All right, so let me go over this formula. So Isaac Newton, 350 years ago, or a little bit more than that, came up with this formula. It says that the gravitational force is equal to a constant. So G is just a constant of the universe. It's called the universal gravitational constant. Times the product of the two masses, so mass 1 and mass 2. I've drawn them both as circles here because a lot of the things that we deal with in astronomy are spherical. And by the way, the reason that they're spherical, and this is a big idea, the reason that a lot of things in astronomy are spherical is because they have self-gravitated into a sphere, right? Right. Anyhow, and this is divided by. Oops, I messed this up, didn't I? So it's divided. So it's mass 1 times mass 2 divided by the square of the distance. Let's make sure that I put that square in there. I forgot about that. The square of the distance. Divided by the distance squared. All right, so that makes a big difference, as you're going to see. All right, so here's our situation. We have two masses they're a distance, and we know in this particular case, the only thing that we don't know either mass, but we know that they're the same mass in each situation. So, imagine, I'll redraw it. Let's say, so that they start off 1 meter. Okay, so in this particular case, we know that the distance is 1 meter, but that's all we know. This is 1 meter, right? And then it says, however, when they're 2 meters apart, so there's something, there's something that's pulling them apart, let's say. So these two masses are now 2 meters apart, right? Just like the problem says, right? Now they're 2 meters apart. So now if they're 2 meters apart, so here, I'm going to try to redraw this. So this is going to be M1. And then let's see, I'll put the other one. So this is approximately twice. This is supposed to be twice the distance. There's M2. All right. And then here is now the distance. All right. So this is some new distance. But we know what that new distance is. So in fact, we'll call this one D sub A for situation A when they're 1 meter apart. And then we'll call this one D sub B when they're 2 meters apart. Okay, so that's all we know. All right. Again, same masses, but they're twice as far apart. All right. And so look, you can actually figure out what's the force between them, and you can compare the two because it's the same masses. The G is exactly the same. All right. So let's do. So in the first situation, all right. So in this situation up here, let's write out what the force between them is. And so this is a general equation, all right? And so the force, and so I'll call this force of A. It's force in situation A, so that's the above situation. In situation A, they are a distance of 1 meter, so the force is, G times M1 times M2 divided by 1 squared. All right, so that's it. And then here, let's look at this in situation 2. So we'll call this F sub B, right? So that's this situation right here that we're talking about, and we know that they're 2 meters apart. All right, and so that's equal to G. And again, it's the same masses, mass 1 and mass 2. Those two have not changed in this particular situation, but now it is 2 squared, right? 2 squared. So and the other thing is, there's similarities between these two, right? It's essentially the two of them. Like force B is exactly the same as force A. Sorry, that's supposed to be an A. But notice, right? It now it's divided by 4, right? So for force B is now 4 times less. So that answers. So look. So it is. Since it's 2 meters apart, it is 4 times weaker, right? That would be the answer, 4 times. So you'd put a 4 right here. So anyhow, you put a 4 right here, 4 times weaker. All right, and you could play little games with this. Let's say that, that they were, let's say they were half the distance. Okay, so here, let me do the problem again. Let's see if I can erase. It'll take me a while to erase all this, but here, we'll do the second situation. All right, so here, I won't have to draw all this again. I'm just trying to get some room. All right, so all right. Actually, let me just start again. Sorry. Here, we'll do this. All right. So now, here. This is what we're doing. All right. So again, if they're 1 meter apart, okay. So this is mass 1. So this is going to be our mass 2. I'll make mass 2 slightly bigger. So remember, it's to the center. All right. So the distance has to be to the center. So this is our situation D sub A, which we know is 1 meter. All right. And so this is mass 2. But now that's a 2. Sorry, doesn't look like a 2. And now let's say that again, it's the same. That's supposed to be the same size. Come on, TJ. Sorry. That's supposed to be the same size as mass 1, or it's just a representation. Anyhow, so here's mass 1. That's a better size. Here's mass 1, and then now let's say it's only half. All right, so here's mass 2, and then let's say D sub B, right? So this is the second situation. Now this is 0.5. All right, or 1/2, right? 1/2 a meter, where this one was 1 meter. All right, so now what's the force between them, right? Remember that the problem was what was the magnitude of the force and what was is it stronger or is it weaker? All right, and so from this formula, right, the general formula of the force is equal to G times the product of the two masses divided by the distance squared. Um, when they're closer, it's going to be stronger, right? When things are closer, they're strong. All right. So, but let's see that mathematically, right? And so here's the situation, right? So this is FA, right? So here's the first situation, and so FA is just it's just G times mass 1 times mass 2 divided by 1 squared, right? And then so that's what F1 is, and then F2, so FB, sorry, that's what FA is. I'm using. I want to stick with letters instead of numbers, just because it gets kind of confusing. Anyhow, for step B, it is this. So it's going to be G times M1 times M2, right? Whatever those values are, if they have to be in kilograms, by the way, if you were to actually use this formula. And then it is, so remember, 0.5 is, of course, 1/2. Let me write it like that, 1/2. And it's meters. But you square that. All right. So now look at what happens, right? So if this value, G, the product of G M1 M2, this value over here, if we compare F1, FA and FB, you can see that this now becomes, look, if the 2 squared you have, here, let me use the mouse. You have what's in the numerator divided by, a fraction, right? And of course the fraction is squared. But see what happens is, of course, the 2 squared comes up to the numerator. So this becomes 4 times G times M1 times M2. So see, now it's 4 times the strength. Remember, this one is not, this one over here for FA is not of interest. So you could rewrite, this G times M1 times M2 is just FA. So it's 4 times FA, right? By bringing them in, by cutting the distance in a half, you've quadrupled the force. The force is now 4 times the strength. So it's 4 times stronger. That's the way that you'd say that. All right. Wow. I didn't think that would take me the full 15 minutes, but of course, we're describing Newton's universal law of gravitation. And G is a constant of the universe. Its value is 6.67 times 10 to the minus 11th. We talked a little bit about that in the first lab. But anyhow, you're not really using that value per se.